Power series. A power series is a polynomial on steroids. When we think of a quadratic polynomial, I think of a function whose highest power is x squared. Cubic polynomial, its highest power is x cubed. I'm going to write a polynomial, instead of highest power to lowest power, I'm going to write it lowest power to highest power. That's a polynomial. That's a polynomial. That's a polynomial. But a power series is an infinite series, like a polynomial. Notice that that series is indexed to start at 0, which means we start with an x to the 0th power, which is just a number. And then I have some coefficient of x to the first, some coefficient of x squared, some coefficient of x cubed, and so on ad infinitum. Now the c's are numbers, they're coefficients. X is a variable. So I don't just have one series here, I actually have lots of different possible series. Because I can put in different values of x, right? Put in a different value of x, I get different answers here. If I put in positive x's, then maybe, depending on the c's, those are all positive terms or not. If I put in negative x's, then all of the even powers of x are positive, but all the odd powers are negative. Maybe it's an alternating series. So instead of just asking, does this converge or diverge, I really want to ask is, what values of x make this converge or diverge? Now, fortunately for me, depending on the values of the c, some of these are series we've already seen before. An example. I've seen that series. N equals 0 to infinity, the sum x to the n. What kind of series is that? Yeah. Well, yes, all of these are power series, but what other descriptor can I use for the same series? I don't know what that is yet. And this one, actually, no. What if I wrote it as 1 times x to the n? It's geometric. And it's a geometric series where a is 1 and r is x. So notice, I now know when this converges. It's a geometric series, Dom. When does geometric series converge? Yes, please look. Grab that flowchart picture that we have on our Canvas page, or whatever notes you wrote yesterday about when geometric series converge. Jacob? Yes, but if actually it's R is greater than or equal to 1, it diverges. So this only converges if R is strictly less than 1. And that's an absolute value. Hey, wait a minute, R is X. So that means this converges when X is less than 1. I just found a whole collection of X's where I know this is going to converge. And because it's geometric, I know what the total is. What's the formula for the sum of a geometric series? Well, that's what the terms look like. What's the actual total, the capital S value? Right, but what is that actually? We have a formula for that. And I know A, and I know R. A over 1 minus R. Whoa, hang on a second. If I put in X equals 0.3, I know what adding this up is. I put in X equals negative 0.2, I know what this adds up to. I put in X equals 3/4, I know what this adds up to. I have a formula for the total everywhere between negative 1 and 1. Now, if I actually use 1, then this series is 1 plus 1 plus 1 squared plus 1 cubed plus 1. That's 1 plus 1, that goes off to infinity. If I put in negative 1, I get 1 minus 1 plus 1 minus 1 plus 1, which keeps breaking back and forth between 1 and 0. So that diverges. So it's only going to converge between negative 1 and 1. I found a whole interval. What values of X make this converge? There's my answer, right there. And it diverges outside that interval. Now, I actually like to think of there being a little bit of a picture here. And that picture is the number line. And the interval, absolute value of X less than 1, stretches from negative 1 to 1. And my brain says, this is the region, the interval, where we converge. I'm even going to call it that. The interval of convergence, IOC. And what's more, that interval has a center. The center of that interval is 0, yes? And I can think of these terms in our geometric series as also being related to the center. I'm going to write another power series. Compare the one at the bottom of the screen with the one at the top of the screen. Okay. The only difference between those two. Yeah. Which means that the one at the bottom is basically a u substitution away from being the one at the top, isn't it? If I wrote u equals x minus 3, then I could write the bottom one as u to the n, couldn't I? Oh, that's a geometric series also. Again, with a equal to 1, but this time r is equal to x minus 3. So where's that going to converge? Geometric series, it's going to converge when r is less than 1. In absolute value. But I can turn that into an inequality in x, so that's x minus 3 less than 1. Now do me a picture. Draw me the version of the interval of convergence for this series. What's your picture of the number line look like down here? Yes, but then the center of that is not 1, right? So let's look at this as an algebraic inequality. Absolute value of x minus 3 less than 1 is negative 1 less than x minus 3 less than 1, right? And that becomes add 3 to all sides. That becomes the interval from 2 to 4. And the center of that interval is at 3. And that center is right here in the original series form of this power series. So the first version that's centered at 0. This version is centered at 3. In general, I can center a power series wherever I want. And really, if I were to write this power series out, I would get C0 and then C1 times x minus a to the first, and then C2 x minus a squared, and C3 x minus a cubed, and so on. Yes? Okay. Remember that our question was, what values of x make this converge? I guarantee you there's at least one value of x where that power series must converge. What happens if you plug in x equals a? Yeah? And then everything else would be 0, wouldn't it? Aha! aha, if x equals a, then this entire power series equals C0. That's a finite number, which means it's guaranteed to converge there. So I can always guarantee you for any power series anywhere, it's got to converge for at least one value of x. It might converge for a bunch more. Like we got that whole interval between 2 and 4 to converge up there. But I don't know for sure if it's going to converge on a big set of x's or a small set of x's or just one x. But it's got to converge somewhere. Questions? My favorite test for dealing with power series is the ratio test. We're going to do that the most. Here is a power series, n factorial x to the n. I would like to know where this converges. Because right now, the only thing I can guarantee, the only place I'm sure this is going to converge is if x equals 0. Because if x equals 0, that's 0 factorial times 1, x to the 0, plus 1 factorial times 0. Oh, wait a minute, 0 factorial is equal to 1. That's equal to 1 when x equals 0. But I don't know if it might converge for other x's. So I'm going to do the ratio test because what's the result of the ratio test? The result is the thing in my ratio test is L, and it converges if L is less than 1. So I need to know for what x's is that limit going to be less than 1. So let's do the ratio test. The limit as n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial x to the n. I would like you to simplify that limit as much as possible. What happens? Yeah.
The n plus 1 times that could be like n factorial and n plus 1 divided by the n factorial. And the x and n plus 1 equate n out to the x by itself.
All of the other pieces in the factorial, other than the n plus 1, go away. All of the other x's except the one extra one on top go away. Perfect. What happens as n goes off to infinity here? So really, it now depends on the value of x, right? If x is 0, this limit is n plus 1 times 0. But that's the limit of 0 which is just 0. If x is anything else, the limit as n goes to infinity of n plus 1 times x blows up to infinity. So the only time that limit is less than 1 is when x is 0. Which means our series only converges for that one value of x. It diverges everywhere else. That's it. That's the only spot on the number line where this converges. It goes kaboom everywhere else. So to me, that kind of looks like a crappy answer. But this was a rigged example. Let's try a different one. Instead of multiplying by n factorial, let's divide by n factorial. Now let's see if I can figure out what's going on with that power series. Okay. I'm going to do the ratio test. What happens this time when you do your algebraic simplification? Almost. The n plus 1 factorial and the n factorial cancel, and all I left behind is an n plus 1. And it's on the bottom. But when I bring this up and flip it over, the x to the n plus 1 is on top. There's an x to the n on the bottom, right? So the only thing that survives on top is a single x. Now wait a second. Pick an x. I don't care what number you pick. Pick an x. The bottom of that fraction is getting absolutely huge, right? What's that limit? It's 0. No matter what. Where does this converge? That's always less than 1. This particular series converges everywhere for all possible x's. You should put a star next to this one in your notes. You're going to see this series again. I like this series. It's a friend of mine. So here are the two extreme possibilities. That top series only converged at the center. This bottom series converges everywhere. What's the other option? X minus 3 to the nth power over n. Please do the ratio test. Tell me what you get for your simplified version of L. I'm sorry, how can I have?
Like conditional convergence, you said it's only converging by x.
Okay, conditional convergence means it converges when the pluses and minuses are put back in. And it diverges when the absolute value is in. That's not the same as saying which x's make this converge. That's the different thing. As a matter of fact, not only does this converge for any x, it converges absolutely for any x, whether that x is positive or negative. But this one only converged when x was 0, because otherwise, test for divergence. So now my question is, when is L less than 1? What does L simplify to? Yeah. Almost. I got to do the limit first, right? So before I can, yes, x minus 3 is correct, but x minus 3 to the n plus 1 over x minus 3 to the n gives me 1x minus 3, but I also have an n over an n plus 1. And when I take that limit, I get the absolute value of x minus 3. So you're absolutely right, as long as we include that absolute value. Now, Maddie, I think this might answer your question. My series is absolutely convergent if this expression is less than 1. Right. What do you know is the set of x's where absolute value of x minus 3 is less than 1. I'm having the weirdest sense of deja vu because I did another series with x minus 3 in it.
It would be like x minus 3 is less than 1 equated to negative 1.
And let's walk through the rest of that.
Then it'd be between 2 and 4 factors.
So my series converges absolutely when x minus 3 is less than 1, between 2 and 4. It diverges when L is bigger than 1, right? So it diverges when we're bigger than 4 or smaller than 2. But wait, there's more. What if L equals 1? Wait a second, say that again?
It's not inclusive.
It's not conclusive. I don't know from the ratio test alone what happens at 2 and at 4. I know it converges on the inside, it diverges on the outside, but right on the edge there, weird can happen. So I need to check those two values of x separately. Oh, wait a minute. Let me write over here. Diverges if L bigger than 1, x smaller than 2, or x bigger than 4. Ratio test is inconclusive at L equals 1. So I don't know what's actually happening for those two numbers. So what do? I run screaming for the hills and say, no, I can figure this out. Let's actually go to the original version of the series and plug those numbers in for x. Which one do you want to do first, 2 or 4? Okay, so if I do x equals 2, then I have 2 minus 3 to the n. Well, that's negative 1 to the n, right? So my series becomes minus 1 to the n over n and goes from 0 to infinity. I'm having the weirdest sense of deja vu. I've seen that occur before. What series is that? Not just any alternating series, that's the alternating harmonic series. But it's an alternating series, so I know whether or not it converges or diverges, don't I? I can do the alternating series test. But, and that's why, Leo, I was very particular to say this is the alternating harmonic series. We already did the alternating series test on that one. I know that converges. If you don't remember that the alternating harmonic series always converges, feel free, do the alternating series test again and write out the alternating series test. Hey, those numbers, if I take away the plus or minus, it's 1 over n, that's always positive, and it's decreasing, and its limit is 0. Check. Passes the alternating series test. What if I plug in 4? Yeah?
Would be a 1 to the n over n.
But 1 raised to any power is just 1, which makes this the sum of 1 over n. Houston, we have a problem. What kind of a series is that? It's not just any p series. It's p series with p equals 1, the harmonic series, which means diverges. Hey, wait a minute. We now know every x where this converges and every x where this diverges. It converges for all the x's between 2 and 4. It also converges for 2, which means my interval of convergence includes 2, but does not include 4. If we were to draw the little picture, there's my center at 3. I draw it like that. I also tend to think of this interval as, since it's centered at 3, it extends out to the left and the right. I think of that as a radius, like it was a little circle. I say, oh, there's a circle here. The diameter of that circle goes from 2 to 4. What's the radius of that circle?
1.
And so I'm going to call that the radius of convergence of my series. Now, I need all of you to realize that in this entire problem, I made a copy error, and none of you called me on it. Way back here at the beginning, I wrote n equals 1. Here, I wrote n equals 0. Why can't I use n equals 0 in this problem? Because I'm dividing by n. So all of those zeros should be 1. Oops. That's an F up on my behalf. Some power series are really complicated. And there's a wonderful example in the textbook on page 700 and 48 of a power series that I'm never going to use again. And yes, just looking at that should make you choke and barf a little. That's disgusting looking. But what this is called the Bessel function of order 0. And what it represents as a power series is a vibration. At the top is a drum head with a bullseye drawn on it. Color coordinates. And at the bottom is the mathematical model for the power series I just wrote down. The vibration of that drum head is modeled by this power series. Holy moly. So power series come up in lots and lots of different ways. And when you look at the overall Bessel function, you get a picture that looks like this. When you see the one big vibration and then how it diminishes as we go out in radius. That's exactly what happens when you strike the center of a circular drum. Questions? If I have a power series, there are 3 and only 3 options, and we've just seen an example of all 3. Option number 1 is that the series only converges at x equals a. It only converges at the center, never anywhere else. Option 2, the series converges, parentheses, absolutely, for all x. Or option 3, there is some value, capital R, a positive number, so that the series converges absolutely for absolute value of x minus a strictly less than r, and diverges for absolute value of x minus a strictly bigger than r. Notice that leaves x minus a equal to r as a question mark, and we will have to investigate those edge cases separately. R is called the radius of convergence, and the interval from where x minus a and absolute value is less than r is called the interval of convergence. Every time, you either get one spot and only one spot, and by the way, we often say if you're only converging at a single spot, that your radius is 0. Because you don't converge anywhere other than the center, you can't go any to the left or right. Your convergence is everywhere. We often say then that the radius is infinity. You will often hear the term entire, that a power series is entire. It covers the entire real line, all the numbers. Or it's somewhere in the middle, between 0 and infinity, some positive number is my radius. Whew. Almost every time, I am going to find my radius of convergence using the ratio test, using the question, where is L less than 1? And I'll figure out the value of R, and I'll figure out the interval, and I'll check the ends. So this is really a 3-step process. Ratio test, and then I check each end, and I might have to do a different test for each end. I could do as many as 3 different tests to figure out the interval of convergence. Questions? Let's do one from scratch. Oh, and on that page that I was just looking at with the vessel pictures, on page 749, there's a table with the examples and what their respective radius of convergence is. Correctly understating that theorem, page 749. Here's our table. So the first thing I need to do when I'm dealing with power series is the ratio test. What happens when I simplify? Jacob? Three x. There's some work in between here and there. How do I get there from here?
Negative root and change some of that. And versus the square root of n plus 2.
I still have the absolute value around the x. And get rid of the absolute value for the 3 when I convert the negative to a positive, and then the limit as n goes to infinity of root n plus 1 over root n plus 2. Yeah, that limit is 1. So what's the radius of convergence? Where does this converge? Ooh, careful. I want L to be less than 1. So I want 3 absolute value of x to be less than 1. That means that I actually want a 1/3 over there. And that's my radius of convergence. So I know that it converges absolutely between those two numbers. The real question is what happens at the edges. Now remember, the original series, minus 3 to the n, x to the n, over square root n plus 1, n equals 0 to infinity. So let's take one end. Do you want to do positive 1/3 or negative 1/3? Okay, so if I start with negative 1/3, then my series is negative 3 to the n, negative 1/3 to the n, over root n plus 1. What happens in the top? Because the 3 and the 3rd cancel, and negative times negative is always positive, right? Oh, wonderful. That makes the top of this fraction always a 1. What type of series is that? I'm going to compare it with what? Which is a p series. Now I'm going to actually, I think the best comparison to do in this case is the limit comparison. And when I do the limit comparison, I get 1, which means both of those do the same thing. So does this converge or diverge? Say again? This is a p-series with p equal to 1/2. 1/2 is smaller than 1. This diverges. So this one diverges also. Now I have to check the other end. But my alarm has just gone off on my phone telling me that class is officially over and I have a meeting to get to in 10 minutes. So I want you to check the other end. I want you to tell me whether the other end converges or diverges. And I will answer all sorts of questions for you tomorrow about power series and about our series strategies and whatever 11.6 was. Ratio root tests. So I'll see you all then.